Dear student, welcome back to the operating system video lecture sessions. In this lecture, we are going to discuss about Dentlak's safe states. In this chapter, we are going to discuss about deadlock avoidance. And the objective of this chapter is to develop a description of deadlock, which prevents set of concurrent process from completing their task, to present a number of different methods for preventing or avoiding deadlocks in a computer system. The outcome of this video lecture is how to handle the deadlock and how to prevent and avoid the deadlock, detection of deadlock in the process, and at last, how to recover the system from deadlock we are going to learn. Right. So let us start with safe state. The safe state is when a process requests and available resources, system must decide if it must have to decide what it have to decide. It must decide if it allocates that particular resources to that process, if that step will leave the system to the safe state or not. So that first thing we have to discuss. And if system is in safe state, if there exists a sequence P1, P2, P3 and so on, Pn of all the process in the system, such that for each Pi, the resource Pi can still request, can be satisfied by currently available resources, and resource already held by that particular process Pj. So already process is having a number of resources, and still if it is requesting from some other resources, if the CPU allocates that resources also, if that will leads to the system deadlock state or safe state, that we have to decide. In that, for that, how it can be achieved. So that can be achieved if Pi resource needs are not immediately available. If it is not immediately available, then process I can wait until Pj have finished, the other process have finished, right? When Pj is finished, Pi can obtain needed resources. If the Pj is completed, it must be allocated to Pi, and it must execute return allocated resource and terminate that process. When Pi terminates, Pi plus can be obtained in needed resources and so on. So if it follows this state, this process, then there is a less chances to get your system into the deadlock states. So that is, we call generally it as safe state. So if a system is in safe state, we can surely say that that cannot leads to deadlock. If system is in unsafe, that means that there is a possibility of deadlock, but we cannot say that if it is unsafe state, it is in deadlock. We cannot say that. So how you can avoid the deadlock, ensure that a system will never enter into unsafe state, just like this diagram. So this is deadlock state, and this is completely safe state. Okay. When your system is inside the safe state, you can say that it cannot enter into the deadlock. When the system is in unsafe state, there may be a chance it may leads to deadlock, but all the unsafe states cannot be a deadlock states. That we have to remember. Right. So first one, we see avoidance algorithm, deadlock avoidance algorithm. if we give single resource to each resource type, use a single resource allocation graph, then there is a very less chances, mostly there is no chances to get entry into the deadlock state. If there is a multiple instances of a resources, if the resources is having multiple instances, then use Banker's algorithm. Now we are going to see this Banker's algorithm next coming slides. Before going to Banker's algorithm, we have to know resource allocation graph scheme. So there is, see, you already done this resource wait for graph, right? Now there is one more edge is called claim edge is going to be added for this wait for graph. So generally PI2RJ, that means that it indicates that process PI is requesting resource J, instance of resource. So that will be now represented by the dashed lines. Previously it was a straight line, now it will become the dashed lines. So we call it as claimed edge, right? Claim edge converts to request edge. Initially it is claimed edge, then it will check the status of the system. If doesn't leads to deadlock, then that will be converted to the claim edge, will be converted to the request edge when the process requested resource, and request edge converted to the assignment edge when the resource is allocated to the process. So when a resource is released by a process, assignment edge converts to the claim edge, and resource must be claimed a priori in the system. So it will be like this. So this is claim edge, and this is assigned edge, and this is requesting edge. So P2 is requesting R1, R1 is already assigned to P1, and P1 is claiming to R2, and P2 is also claiming to R2. Right? This is resource allocation graph. Now, unsafe state. See, if P1 is requesting R2, that is claiming R2, and which is already, that R2 is already held by the P2, and P2 is requesting to R1, and R1 which is held by the P1. Here you are taking it as a claim edge. Claim edge means it has not assigned. So by seeing this claim edge, it will become a cycle. So if it is a cycle, then it leads to the deadlock. Immediately system can find out that if it is assigned, then it cannot be in safe state. So it will leads to the deadlock, so that we cannot assign this resource, right? So in that way, you can avoid the deadlock. Right. So coming to now Banker's algorithm. So Banker's algorithm is a resource allocation and avoidance algorithm that tests whenever, if safe states, the system is in safe state or not. Safe state or not. So there are some data structures used to implement this Banker's algorithm. So let us see. Let n is the number of process in the system, and m is the number of resource types. So these are the data structures: available, max, allocation, need. These are the data structures. Let us discuss one by one. Available, a vector of length m indicates the number of available resources of each type. If available of j is equals k, there are k instances of resource type rj is available. So that is available data structures, right? Next one is max. Max is an n by m matrix. It's an n by m matrix. Defines the maximum demand of each process. Maximum demand of each process. If max of I and j is equal to k, then we can say that process Pi may request at most k instance of resource type Rj. So that is max data structures. Allocation. Allocation is also an n by m matrix, defines the number of resources of each type currently allocated to each process. If allocation of I and j is equal to k, then process Pi is currently allocated k instances of resource types to Rj. The last data structure is need data structure. It is also an n by m matrix, indicates the remaining resources needed of each process. If a need of ij is equal to k, then process Pi may need more instances of resource type Rj to complete its task. So need will be calculated based on this. Need of I comma j is equals max of ij, and allocation of ij. So with this, you are going to calculate the need. So this is generally the bankers algorithms data structures. So in the next lecture video, we'll discuss about one more safe state algorithm.